All right. So today we are discussing the primal bounds. Continue the discussion from the previous lecture. I will go over a couple of examples. Some of them resemble of the problems that I have prepared for the homework. The homework is going to be posted after the discussion. So first of all, the problem from the chapter 13 on heuristics. Remember the generalized assignment problem that we discussed during the lecture, where you have jobs, and each job can be performed by multiple workers, but there is a threshold on what exactly how many workers can work on the same job. That can be expressed as a linear constraint. We have a particular example here. We are given specific matrix C and the specific matrix A that again that the values for the vector B, and we are asked to devise a heuristic. It's kind of a vague statement for a problem, and I'm gonna present you with what exactly how you can proceed when you're asked a question like this. So first of all, a heuristic should include a way to find a feasible solution and a way to improve a feasible solution. So first of all, finding a feasible solution. Taking a look just by looking at this gap problem, you can see that it requires you, if you're so a feasible solution, you just forget about the objective function. You just worry about the constraints. The constraints require you that in the matrix Xij, you like in each row you have a single unit and a single zero. Like in case of n equal 2. It's a 1, 1, and 1, 0 for each row. If n is greater, then you have a single unit, and all other entries are 0 in a row. On the other hand, you have inequality for a column. So for a column, the sum over Aij's where we have ones on the matrix X, the sum of Aij's should be less than or equal than B. Like the corresponding B. We would need to take that into account. And one way to do it is to consider this matrix Aij and take the smallest Aij in each row and set the corresponding Xij to be equal to 1, just because we are hoping that the smaller Aij's are hitting the sum, the smaller is going to be the sum itself, and therefore we will satisfy this constraint. So if we are not successful with that, we can just take the largest. So if there is an inequality that is not satisfied, we can take the largest value Aij that hits the sum and try in that particular row we can flip the position of the unit. So let's take a look at the example. What the strategy would result for this particular example. The initial solution is going to be, and the initial solution for X, it's going to be a matrix 1, 1, 1, 0, 0, 0. For each row, we are picking the smallest value Aij. So if we are writing down the summation for a column, then here it would be equal to 5 plus 5. Here it would be 10, and here it will be 0. And we see that 10 is in fact greater than 6. Therefore, the solution over here isn't feasible. Therefore, according to our strategy, we are finding a column where exactly it's infeasible, and for that column, we are finding the largest value for A, which is going to be 5, and we are flipping the position of the 1 for that particular value, for that particular row. So instead of locating 1 here and 0 here, we'll flip, and it's going to be 0 here and 1 here. Now you can recalculate the summation over the columns, and take a look at that. It's going to be 5 and 7. 5 is less than 6, and 7 is less than 21. Therefore, this solution is feasible. So our heuristic will result in a feasible solution. How can we design strategy to improve the feasible solution? Well, the only thing we can really do is we can pick rows and change the position of the unit in each row. So we need to do it so that on each step, each time we flip something, first of all, the resulting solution is still feasible, and second, the resulting objective value is larger than the previous one. Take a look at the example. So in this particular case, we are having so our previous solution is this one. We are picking the second row and flipping the bit into a different row. We are resulted with the next solution x, take x dash, which is 0 1 0 1 1 0. So our solution remains feasible, first of all, because 7 plus 8 is less than 21, and C22 is equal to 19, which is greater than C21, which is equal to 15. Therefore, our new solution is better than the previous one because we have improved the value of the objective function. We can try to do the same thing with the first row, and this will not bring us a feasible solution. If we flip now the bit in the first row, and we can try to flip the bit in the third row, which will give us a solution that is worse than the previous one. Since we cannot find a row in which we can flip the position of the 1, we can stop here and conclude that our heuristic has led us to the best solution in the neighborhood, or basically we have demonstrated the performance of the heuristic, and it gave us a value. It didn't have to be the optimal one, just a feasible value. Okay. Any question regarding how to design a heuristic? No questions. Cool. The next problem is going to be the next example is going to be focused on uncapacitated facility location problem. We had it during the first discussion section, but I did not stop on it. Like it was in the very last portion of the slides, and I didn't go over that during the discussion. You could have seen it at home, but I will just remind you what exactly this problem is about. So you're given a set of potential depots and a set of clients, and you suppose that there is a fixed cost Fj associated with the use of depot J. And then transportation cost Cij, if all of clients ice order is delivered from depot J. The problem is to decide which depots to open and which depots serves each client so as to minimize the sum of fixed and transportation cost. This problem is similar to the covering problem in a way. So how we can imagine this problem yourself is having a bipartite graph. You have the depots and you have clients. and you have a matrix that is connecting some Cij that depicts the relationship between the defaults and the comments. And also you have a fj, which is a cost associated with operating a particular default. So if you have decided that you will utilize some of the edges that connect the default J to some clients on the right-hand side, you will have to suffer the cost of fj. Any question regarding the formulation? Okay. So the variables here are the fixed cost of opening, so it's basically the first variable x is the binary variable that signals if a default j is open or not. And the yij is the fraction of the demand that client I satisfies from default j. The definition of the constraints. So first of all, we have to satisfy all of the demand that customers actually has. So the sum over all defaults of yij must be equal to 1, just because yijs are fractions of the demand. To represent the length between iij and the variable j, we can use we can say that we have some large number m that is the larger than anything else that we have in the problem, and we are saying that the summation of yij must be less than or equal than mxj, which means that if any of the yijs for any I, if it's greater than 0, then xj must be equal to 1. Otherwise, xj can be equal to 0. And since our objective function is the minimization of the cost, xj will try to be as close to 0 as possible, and it cannot just jump over to 1. So this enforces the relationship between yij and xj. Any questions on the constraint? So the objective function is minimization of the total cost. So yij is connected to enters the objective with the coefficient Cij, and xj enters the objective with the coefficient fj. Right. There is a caveat here. So we have formulated our constraint as a sum. However, there is a better formulation. So logically, these constraints just express that for any yij, if yij is greater than 0, then xj is equal to 1. Or otherwise, for each I, if yij is greater than 0, then xj is equal to 1. Therefore, we can just restate it as like, instead of having m constraints with the summation, we can have more constraints for each I. We can have a different constraint. So we'll have n times m constraints, but they're going to be like, each of the constraints is going to be much simpler, just saying that yij is less than or equal than xj, just because yij cannot be greater than 1 anyway, and as soon as yij is greater than 0, xj must be equal to 1. So our reformulation, the final formulation, takes the following form. We have m constraints for each client, that is telling us that its demand must be satisfied, and we have m times n constraints of a very simple form that is saying that yij is less than or equal than xj. Then we have non-negativity constraints and the constraints of xj being binary. This is the final formulation for the uncapacitated facility location problem. And we would like to try to approach this problem to attack it with a greedy heuristic. Just a reminder what greedy heuristic is. We are choosing the element whose additional cost per unit of resource is minimal. So on each step, we are picking like this element. If addition of this element to our bag of elements is feasible, then we do it. We just grab this element. Otherwise, we skip it and continue to the next one. We never reconsider taking anything out of the bag. So this process is kind of is a single go algorithm. So we have an example, a particular values for the cost matrix Cij and the vector f, and we apply the greedy heuristic to an instance of the uncapacitated facility allocation problem with m equal to 6 and n equal to 5. In our case, the function v from the greedy heuristic is going to be the total size of the set S, and essentially just because we don't really have a single constraint here that must be satisfied, we just assume that each element that we are adding to the bucket is equal, have an equivalent weight. So what is an element in this particular interpretation? An element is going to be if we are adding a depot or not, because the complexity of this problem is coming really from the binary variables, and the only binary variables we have in the problem are xj's. Therefore, S is going to be a set of j's such that xj is equal to 1, or in other words, S is the bag of depots that we have to open in our scenario. So we are essentially minimizing the function v takes care of the number of depots that we have opened. Okay, so initialization S. The S0 is the empty set, which is an unfeasible set, but we need to start somewhere, so we will take that. Then our cost function is gonna be the original cost function. So it's the summation overCij's of fj's. After that, we are considering adding every single element to our set S0, which in our case, if we are adding the element number 1, what happens then? Well, if we consider that all the xj's are equal to 0, but the first one, what can we say? So our xj, x1 is equal to 1. Then we know that yij's, the summation of yij's must be equal to 1. Therefore, and moreover, yij must be less or equal than xj. Therefore, the only yij's that can be greater than 0, yij greater than 0, only if j is equal to 1. Just because otherwise, if j is not equal to 1, then yij must be equal to 0 because it's bounded by 0. And from this, you can conclude that, and also you know that summation over j's of yij must be equal to 1. Therefore, from this fact, you know that I1 must be equal to 1 for all i's. So our matrix yij takes this form. It's going to be all 1s and then 0s in it, like in all other columns. So in the first column, it's all ones, and then it's zeros everywhere else. If you, so this is the only feasible form for Yij. If we are only considering x1 being equal to 1. So this actually gives us, since we have only one feasible point, this gives us exactly the form of the objective function. The form of the objective function is the summation of all of the numbers in the first column plus the first value in the vector f. And this is what you can see. The C of 1 is the summation of the numbers in the first row plus 21, the first loss, and it gives us 63. Any question on how that is calculated? Okay. Similarly, we can calculate the C of 2, C of 3. So you just change this 1 to be 2 or 3 or 4 or 5, and eventually you can see that our C3 is the minimal, the 59. It's the minimal loss that we suffer, and moreover, it is there is a feasible solution that corresponds to the set S1, which is equal to the 3, the unit set 3, and it is a feasible solution. So we define S1 to be equal to the set that consists of the signals element 3. Now we consider adding another element. We have since we have added 3 so far, we can add 1, 2, 4, 5, or 6 into our bag. So let's see what happens when we add 1. When we add 1, we need to consider the addition. So I will just remind you. The algorithm, the greedy heuristic, considers the difference between the objective function C at the case when we have added an element to our bag, and in the case we have not added the element to our bag. And the function V, the difference for V can be ignored in our case just because we set V to be this much, and therefore for any J, no matter what is the element you're putting into a bag, you will be divided by 1. Therefore, you don't have to care about it. So we only care about the difference between the objective function after we have added an element and before we have added the element. This is essentially what is written here. So the CO13 minus CO3 is the difference between the objective values in the two cases, before we added 1 and after we have added. So after we have added 1, we have x1 being equal to 1 and x3 being equal to 1 too. Now you can change this to depict that. So either j equal to 1 would result in Yij being greater than 0, or j being equal to 3 will result in Yij being greater than 0. And then you have the summation over all j's of Yij is equal to 1. You know that only for j equal to 1 or j equal to 3, Yij must be can be greater than 0. Therefore, you can just write it down as summation of yi1 plus yi3 equal to 1. So this is your constraint. So since y is not restricted to be binary, they can take any value between 0 and 1. However, if we take a look at the problem, we can argue that So my statement is that either yi1 or yi3 must be equal to 1, and the other thing must be equal to 0. Why is it so? Well, if we assume that, for example, each of that there is some I for which yi is not equal to 1 and yi1 is not equal to 1 and yi3 not equal to 1, so they are both fractional. Then yi1, we assume that c i1 is greater than c i3. In this case, we would suffer less loss. Let's skip to probably to here, right? So we would suffer less loss if we were to put more weight on yi3 in this case, and therefore yi3 should be increased over yi1, which can be done because both of them are fractional, and this procedure can continue going as soon as we are we have hit the yi3 being equal to 1. In other words, there is a way to show that if our coefficients ci1 and ci3 are not identical, then the solution where yi1 and yi3 are both fractional is not optimal. Is there is it obvious to you how to do this? Or if it's not obvious, let's do it, because it's an important exercise. It makes sense, right? Okay. So it cannot be optimal if these two values are different. Moreover, if they are not different, if they're the same, then it doesn't matter how exactly you weight out these numbers. Therefore, you can safely assume that one of them is equal to 1 and the other is equal to 0 always. Therefore, and moreover, depending, so which one is going to be equal to 1, which one is going to be equal to 0? Well, the one that corresponds to the minimal value of c is going to be equal to 1, and the one that corresponds to the maximal value of c is going to be equal to 0. Therefore, into the objective function, we will take only those values that are minimal between ci1 and ci3. We will take the minimal one. Therefore, our value of c13 is the summation of minimums. The summation of minimums of numbers in this column, in the first column and the fourth column. So these are the values of ci1 and these are the values of ci3. And between these two values, we're picking the minimum, right? And the minimal one enters the objective function with the coefficient of 1, right? And therefore, this is how we write down our objective function, the summation of minimums. And then in the very end, we are adding to that the F1 and F3 that correspond to the elements in our band. And in the very end, we are subtracting C of 3, which is 59. The eventual result for C13 is 12. For C23, it's 3. For 3,4 is 21, and for C of 3,5 it's -1. And it's clear that the 3,5 is the best option because it's minimal. It's equal to -1, and therefore the next bag that we are picking for ourselves is S2, which consists of two objects, 3 and 5. Similarly, you can see that C of 3, 5J using the same kind of argumentation. You can also show that for 3 values there's also there always will be an optimal solution for which two of the values of y are equal to 0, and the one the only one value for y is going to be equal to 1. And similarly, by producing a similar calculation, we can show that none of the differences here is smaller than 0. Therefore, there's no way to add on to 3 and 5 to improve the value of the objective function. Therefore, our greedy solution for this problem is in fact 35. So this is our eventual result for the x, the vector x is going to be take the form 0, 0, 1, 0, 1, and the vector y is easy to calculate from this. Okay, any questions on this example? No questions? Cool. The next example that we are going to be discussing is the maximum weight forest, or the maximum weight tree. A maximum weight tree, or a forest, is a corresponding subgraph. So okay, given a graph with weighted edges, for each edge we construct a cost or a weight. A maximal weight subgraph is a subgraph that of particular type with the summation of edges to be maximum, right? So any questions regarding the definition? So we have this problem, the problem of finding the maximal weight forest. So do you know what a forest is, generally speaking? It's a collection of trees, right? So we are asking ourselves, what is the maximal weight forest? And this problem can be formulated as an integer programming problem, and we can construct a greedy algorithm. We can construct a greedy heuristic, but later on we will see that it is in fact an algorithm. So it's it will converge to the optimal solution eventually, the global optimal solution. But right now we just need to consider what exactly is the heuristic. So the initialization for this problem is the set of all edges. So we are picking all of the edges. So in this greedy algorithm, we're going to be tracking two subsets. The first is the subset of edges, E0, and the second is the subset of the edges in the tree, the T0. We are picking the E0 to be equal to the set of all edges, and the T0 to be equal to empty set. So our current tree is empty. We order the edges by non-increasing weights. So our weights are going to be noted with C from C1 to CM. On an iteration T, we are going to be adding an edge that has the largest weight so far, such that we're gonna be checking if the resulting set of edges forms a cycle or not. If it doesn't form a cycle, then we do add this new edge to our tree, and otherwise we just skip it and remove the current edge that we just considered from the set of edges, from the set of edges that we are tracking. As soon as we have reached, as soon as our number the total number of edges reached n minus 1, and being the number of vertices in the graph, we stop with our t being the output of our greedy heuristic. If our t is equal to m, if we have reached the end of the list of edges, then we need to stop because we couldn't find a tree at all. To obtain the, like, if you're not if you're not interested in tree, then if you just need a forest, then you just need to stop as soon as ct plus 1 is less than or equal than 0, because at this point any edge that you're adding to the forest wouldn't help you, wouldn't increase the weight. Let's take a look at the example. So if we are considering, this graph here, and what we do is we are ordering the edges from the largest to the smallest. The first one is going to be 3, 4 because it has the weight of 12. The second is going to be 1, 5 because it has the weight of 10, and then 5, 6 because it has the weight of 9, and so forth. So we can line them up, and with pluses we denote the edges that will eventually fall into our graph. So the first 4 edges can be added. So once we have added the first one has to go in because it cannot form a cycle. We cannot form a cycle with just one edge. The same thing for the second edge. The third edge and the fourth edge, we can check that they do not form a cycle. So it's 3, 4, 1, 5, 1, 3, and 3, 6. Sorry. So it's 3, 4, 1, 5, 5, 6, and 3, 6. So not like they are forming like a star with an additional edge. If we consider the fifth edge, 5, 6, right? The new edge for 5, 6 will in fact add as a cycle, because this edge, and this edge, all of them will appear in our graph. Therefore, 5, 6 would not be added to the graph, and then 6, 7 will be added. 5, 7 will add. So after we have added 6, 7, 6, 7, 5, 7 cannot be added because it will add the cycle of this form, and so forth. So the 2, 6 can be added, and all of the other cannot be added because they either will form a cycle, or we actually need to stop just because we have added enough edges to the graph. So this concludes this particular example. So in this case, we didn't even have to formulate the functions c and the function v. So our function c was the cost values, and our function v was the number of edges. So we could ignore v once again, just because it didn't like the difference in v's was always equal to 1. Therefore, we didn't have to write it down, and the difference in c's was taken care of because we have ordered. So we have implicitly considered c's already, because we have ordered our edges from the largest one to the smallest one. However, it does fall. This procedure does fall into the overall framework of greedy algorithm that we have considered before. Any questions here? No questions. Awesome. Okay. So this is it for today. If you have any questions, I'll stick around for another 5 minutes. Thank you very much. So the homework is going to be posted after the discussion section, and it will be due after, like, in 2 weeks. Yeah. So